Today I've learned a new trick with OpenOffice. When you press F5 to display, and it only shows you the presentation console and not your slides, what you need to do is go into the slide settings, go presentation display 1, then go back to the presentation display 2, and then it works. So this is a new OpenOffice bug, but luckily it hasn't, crashed or segfaulted or suddenly decided to take 10 years out of the document. So I am tempting fate here. So we're now waiting for the magic smoke to escape from the laptop. Cool. I'm here giving a talk that I could not resist coming up with this title because you have a great sort of interesting thing if I brought out a box of sugar cubes and offered you one. Would be excellent, appropriate. And I've not done it yet just because I keep thinking federal police will get me, but it would be rather hilarious. So I've called Dropping Acid, Eating Data Web 2.0 Cloud World. And this is a bit of a talk exploring the data consistency models of systems and sort of what this means, for applications that we may be working on. And I'm not talking about data models, so I'm going to talk about a bunch of different storage systems, and I'm not talking about the various methods of different data models of storing things, relational, non-relational, all on a text file, on the back of a napkin, somewhere down the back of the couch. Excellent place to store data, especially everything to do with tax returns and the like, or receipts for expense reports. So I'm not talking about what the data models are suited for. I'm talking about data consistency, as in, will it eat your data? So if you wanted a session that was just how to make my Web 2.0 cloud app for next generation web fanboy technology preview beta, this probably isn't the talk for you, and instead you should go to somebody else's who's talking about, I don't know, Mongo. So, dropping acid, no actual drugs here, sorry. We're just going to talk about acid as in the database theory version of acid. I currently work for a company called Percona. I'm the director of server development there. I run a development team that works on something called Percona Server. We also do development on other plugins, Percona Server and MySQL. We also do extra backup, which is online backup for InnoDB, non-blocking, which is all kind of cool stuff. So I have lived my life inside database server development. I'm one of the core developers on Drizzle. Previously worked for Rackspace and then Sun, then Rackspace, working on Drizzle. Previous to that, way back in the day, I actually worked for MySQL, hacking on MySQL Cluster. So a number of the things I did there was geographic asynchronous replication, which sounds tremendously fun when you think about you have a synchronously replicated high availability clustered database, and then you want to replicate from that to another one over a wide area. So you have one cluster in US, one in Asia, one in Australia, and you want to do asynchronous replication between them, but synchronous replication inside each of the clusters. And then you want that to be highly available over multiple links and multiple machines. So I worked on developing that. As you can imagine, you have some kind of uptime and stability requirements there. Generally, the customers who use the software measure loss in millions of dollars per minute. As in, you get a call and say, right, we had an outage of 35 seconds, why? That cost us X many dollars. The joke was, you still had things running mobile phone networks. Some mobile phone networks are not nice parts of the world. So the joke was, if you screw up, you get to go to on-site support there. Where this thing bombs out the back of planes. Never actually happened to anyone, but it was good fun. I also worked on online ad node, so the dynamically expanding cluster. Worked on a bunch on online backup, so working on the online backup module inside MySQL Cluster, including I also did something called NDB info, which is basically getting statistics and information out of the cluster on that, how it was running, what resources were being used. We managed to do that in a way that very much had minimal to zero effect on the cluster itself, actually getting statistics out, which was actually kind of a neat thing to do. I even worked on a Win32 port, so I've actually got good reasons to hate Windows, all of which is Win32 API, and previously to that was inside a kernel debugger. So my most recent experience of Windows beyond 3.11 includes a compiler, a debugger, Win32 API manuals, and the kernel debugger, which is not your typical end-user experience, but I think it's not any nice. One of the joys of this, though, was MySQL had the best group name ever for a team inside the company. We had a Windows task force. Take the first letters of each of that, and you have WTF. So it's always great, because /join, #WTF. It was hilarious. So this talk comes from actually one a few years ago. So back in 2007 at LinuxConf.au, actually before that, before Linux Config 2007, so sometime in 2006, some piece of software ate some data I quite liked. And I got annoyed. As in like, damn people who can't write software applications. So what do you do in this situation? Well, 1, file a bug. 2, actually tell people what the problem is. And 3, submit a talk to LCA about how all your code sucks and I hate you. So I had this idea of a talk called Eat My Data, How Everybody Gets POSIX File I/O Wrong. I also gave this at OSCON in 2008, which is, a bit updated and jazzier and with, 3 more jokes and all of that kind of fun. And it came across the basic idea that most programmers cannot write a file safely to disk. If you give a task out of, 100 programmers and say, write a file safely to disk, I bet you 94 of them will get it wrong. The 6 others are the random ones you've selected who hit this problem in the past or who wrote a file system or something like that. It's actually a really interesting problem to have because a world without failure doesn't exist, right? I mean, computers crash. Your laptop battery runs out. It doesn't do the magic let's shut down for you thing. Power fails. Sometimes the power goes out. Sometimes UPSs don't work. Sometimes the signal from the UPS to the computer saying no, shut down now, I'm about to lose power, doesn't work. Generators fail. I mean, what's great, we've got UPSs and then generators to keep it running, but no one checked that, the generator would start up. Or
sometimes the UPS isn't turned on.
Sometimes the UPS isn't turned on. Sometimes it's great sitting there in the corner and not plugged in. Sometimes the computer needed to be unplugged because the vacuum cleaner needed to be plugged in. What else is there? Sometimes the coffee can spill into the server, which is really actually someone's machine under the desk. So a world without failure doesn't exist. If you're in that last group, you probably have more problems than just writing files safely to disk. But there's definitely this problem. One of the most interesting ones is, that comes up again and again, is something that's pretty simple. I love it. Put Unix man page sections in my talk slides. Close and rename do not imply sync. So if you're closing a file and renaming it, as in going along the idea of, I'm going to write to a temporary file so I don't disturb my last known good data, and then rename, close and then rename does not imply sync. So you may rename, and the rename may hit the disk, but the data in that file may not have hit disk if you crash. So this idea of write to a temporary file and rename, by itself there, this is very, very interesting. What also makes it interesting is the fact that it just so happens that a specific journaling mode on ext3 makes close and rename end up being actually a sync in there as well, right? So it commits it in a specific order. Now this is really odd because a bunch of people think the data is safe, but what they really are saying is you can only run on certain file systems in specific journaling modes to actually have data safe. And we'll try and tell you that, you should just use that. Which is amusing because sometimes you'll say, well, what about NFS or like any other file system, or maybe if it's on a USB stick or anything. So there's a whole bunch of problems here. So the big summary of this talk was write, close, rename equals fail. Very simple to remember. What you want is write fsync close rename equals win, right? Because if you actually say, I want to write the file to disk, I want to sync it to disk, so the data of my new file I know is on disk, then I can close it and rename. And if you want, you can do a sync on the directory, so the directory entry hits disk as well, and you ensure that hits disk. But if you actually do the fsync here, when the rename essentially hits disk, if you crash at any point after this code is called, you'll get either the new or the old. Right? But you definitely won't get nothing, which is really sad when you get a file full of nothing, or a file full of random bytes that were previously on the disk. That's a whole bunch of fun, but I believe most systems now try and avoid that, except for some specific modes in some file systems. So definitely think fsync, 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 fsync. You then have a whole other bunch of problems with fsync, meaning disks lying to you, operating systems lying to you. For example, on Mac OS X, fsync does not sync. Sync, Apple, Epic fails. Some kind of brain-dead monkeys are over there making sure that all your data goes away. Because what would we do? We'd drum into people and now run fsync, call fsync, sync your data to disk, otherwise it's not really there. You'll crash and lose your user's data. And then someone with an assignment due the next day will hunt you down and stab you to death repeatedly with a hammer. Yeah, think about it, yeah. Have you ever gotten that feeling when the data goes away? All right. So someone at Apple decides that fsync doesn't actually do it. And why? Because if applications call it fsync, they're slow. And it's like, well, yeah, you have to wait for spinning Rust. It's not fast, right? I mean, it's like there's a penalty to be involved for actually doing work and having data stored. It takes some time, and sometimes you'd like to think that your important document is worth something, and that when you hit save, you really want it to save. You didn't just mean kind of maybe do it in the next 5-10 minutes. Now. Thanks. So this is actually, it comes down to an interesting issue. We have this wonderful thing called POSIX, which has a lovely thing called a POSIX compliant fsync. So if you read the POSIX spec on fsync, this is a perfectly valid implementation of fsync with one bug. Can anyone spot it? This is actually brilliant. The first time I gave this part of the talk, part of the Eat My Data talk, I did actually have someone yell out and heckle it. It was great.
Should it set NO not implemented or something?
No, it should probably set NO to 0. It's probably really what it should. But, you know, having a bug in like some of your OS calls is perfectly valid implementation choice that most people decide to have when they implement operating systems.
Is it something to do with the instead of integers, you should be using some sort of defined type of, you know, the type of the file descriptor or the type of...
No, it's fine. It's really setting NO to 0 is really what's kind of missing from general good behavior.
Maybe importing EBAD FD if FD is negative.
Probably. But it's possibly ambiguous because the spec does say it's explicitly written to a null implementation is valid. So exactly what a null implementation of fsync, whether it should check whether the FD is valid or not, it seems to be a little bit ambiguous, I think. So probably both are valid, but I think this is possibly the minimal one that would be valid. But what you should check in your applications, of course, according to POSIX spec, I think this came in Unix 99, so for some older Red Hat releases at least that was still in production when I was originally looking at this, was sweet out of luck anyway. But there's a POSIX, if you have a defined set POSIX synchronized I/O, then you could be sure that fsync would actually do a real sync. This is, of course, existing in a world where each operating system only has one file system that implements that specific behavior, because so define at compile time is obviously true of runtime on whatever file system you're running. So we're a bit equally screwed, but don't think about that too much. You can probably safely assume fsync works, apart from OS 10. Go see my previous talk slides for the 3 pages of code that is required to implement proper fsync in OS 10. You think, maybe the Windows guys have got this better. Is the grass greener on the other side? No. So part of the great thing we discovered when doing NDB port is the Windows API has some wonderful calls. For example, get file size. If the function fails and LP file size high is null, the return value is invalid file size. Get extended error information called get last error. When LP file size high is null, the results returned for large files are ambiguous, and you will not be able to determine if the actual size of the file. It's recommended that you use get file size X instead. X, I think, is because I broke up with my last operating system API. That's my X. Invalid file sizes, of course, will get set because having an API that can work for compilers without 64-bit numbers when you want 64-bit file size is obviously something you needed in the 21st century. So, you know, that's a bit of a problem there. Unfortunately, across the world is not everything is simple POSIX apps. So this is part of the idea of going, well, if we get file I/O and safely writing data that is so horribly wrong when it's a simple, you know, word processor, how are we going to deal with in a larger world? Mainly, we're not writing sort of, you know, POSIX C app. We may be dealing with the web. So the modern web has many, many, many moving parts. I mean, who here writes all their websites in straight C? No, not me. Not since the late 90s, anyway. C++ recently, yes, but not straight C. Libevent, by the way, you can do really cool things with the HTTP server if you want to know to write website server C++. So there's many moving parts to the modern web. So if you think about the word cloud, which really just means you're more than one computer now and you want to get funding for buzzwords, which is a great way to get money. I mean, I think there's, at least a dozen companies who got VC capital just in the fact of mentioning the word cloud somewhere several times. Think about that as also a modern strategy. My theory is that people used all the existing shapes in PowerPoint and we're just left with the cloud left, and it's like, well, we better do this now. We've already used, the circle for the internet and the square for a computer. Okay. So modern cloud has very, very many moving parts, and of course, lots of marketing bollocks. So everybody gets simple POSIX apps wrong. So an extra cloud layer of abstraction and virtualization and like extra data storage things and 15 ways to store different bits of data and end client applications and web and that's going to make it a whole lot simpler, because if there's everything we've learnt from the past several decades of computer science, it's that an extra layer of abstraction always makes things easier and more transparent. So some of the systems we're going to look at, and some of the systems that are used in sort of modern cloud apps and even modern web apps, have some dubious care for your data, using some very nicely old sort of updated ideas of what kind of works. And you have some wonderful systems that are very cool, but obviously not written by anyone who's ever read a single paper on databases in their life. And definitely not looked at any implementation. So, we're going to talk a bit about ACID, where atomicity, consistency, isolation, and durability, which is a wonderful word that you can just talk about casually and disguise the use of some restaurant serving LSD. So we're not talking about that. We're not talking about wonderful, wonderful acid in bottles. We're talking about this one. And we're also going to talk about the CAP theorem, which is otherwise known as Brewer's theorem, which just basically says that it's impossible for a distributed algorithm to provide all three. Consistency, that is, different nodes can all see the same data at the same time. Availability, for example, node failure doesn't prevent survivors from serving data. And partition tolerance. So the CAP theorem is that a single algorithm cannot provide all three. It doesn't say that a single system can't, because a single system could have more than one algorithm that would let you choose how much you care about any specific bit of data. Because if one thing we've learned, more configuration options are obviously a good idea. So the CAP theorem is something pretty common to anyone dealing with distributed databases. This is something that's you would think is fairly old hat, but it's generally considered the fact that every single distributed database out there has some problems that you just haven't hit yet. And usually this comes in like usability, whether it's stability, whether it's documentation, whether it's performance. You have all these kind of nice things going on that usually people discover 6-12 months after implementation rather than immediately. But that's true of all software, right? Everything works fine until you actually stress it. Because it turns out software has bugs. We're going to talk about, first, traditional relational database management systems. So let's just look at the bog standard, old, boring database servers. Let's look at MySQL and what that is about. We can also, the same thing goes for like MariaDB and Drizzle, mainly because they all have the InnoDB storage engine as a background. And this basically translates to Postgres as well. We're not going to talk about MyISAM, if anyone still uses MyISAM in a MySQL install, because non-transactional, non-durable, not really interesting. And people are generally still using MyISAM by accident. The same way you still have a Solaris 7 box running, like by accident, you haven't fixed it yet. So we're going to talk about InnoDB. And there's one important thing to think about in these relational database systems. Commit is commit to disk. So when commit returns, your transaction is, have you tried turning it off and on again safe? That is, when you get the commit response back to the client, if you pull the plug immediately on the server and then plug it back in, your transaction is there. It is durable to the machine rebooting, power going out, that kind of thing. It's of course not durable to coffee being poured on the disk or being, shot at by bad guys. But it is durable to a single disk commit. And this is even on OS 10, which tries to screw you. And that was a great bug for someone to find and fix. So it is consistent. You can get a consistent view of data, of course, because you have repeatable read isolation level. The SQL standard isolation levels are tremendous fun reading for maybe me and 12 other people on the planet. But someone else also interested? Yay! A few people. So we have consistency. We can do consistent views of the database. We can get a consistent backup, because of course we can open a consistent view of the database and dump things out. We could even do it without taking a lock or doing a SQL dump. We also have constraints to keep your data logically consistent too. So that can help prevent against naughty programmers. For example, foreign key constraints can sort of make sure that your data has some relationship that is perhaps consistent between different parts of it. So when you have app programmers going off and doing mad, insane things, you don't end up with dangling rows and that kind of thing. And it could also help prevent against like buggy code. And of course, when you're using transactions, you can get either all this happens or not. If you do logical changes inside transactions, you then get some other assurances of consistency that's above what the database provides. It's consistent according to your application's rules. So how do we eat data with normal relational database management systems?
Install libeatmydata.
Install libeatmydata. So for those who don't know, I wrote a shared library called libeatmydata. You LD preload it. There's a Debian package that gives you a command line tool, eat my data. It provides a OS 10 compatible fsync.
Significantly speeds up build.
Oh, significantly speeds up databases. Like, oh my god, off the wall speeds up databases. I use it all the time for my databases, mainly because I run the test suite, and you don't actually need it just be durable to machine crash. You can just run and make tests. So libeatmydata is a great way to eat your data. Some people had this as a great solution to Firefox being slow with whatever, and it's like, you realize all your bookmarks are going to go away if your machine crashes, right? But check it out if you run stuff in test. Do it. It's awesome.
It's great for building Debian packages in a tree.
Yeah. Yes.
Run the whole thing because you don't care if it gets blown away.
Yeah.
Just run it again.
Yeah. Same thing. Make tests. Or if you have a test suite for your app that connects to a database server, and that's a test one, just run it with like libeatmydata and then just blast it away every time the machine boots. Brilliant. Also saves your laptop battery life when you're hacking online. Cool. Let's talk about eating data with MySQL replication. MySQL provides asynchronous replication. So it is possible to have a commit go to local disk and not make it to the slave if the master crashes before that transaction is sent over the wire. So there's a couple of ways to sort of get higher availability with that. For a start, you just have to sort of exist with the basic setup that if the master crashes at the wrong time, you may lose, however far the slave is behind of pulling stuff over the network, which may be maybe a second, which can be different to how the slave is applying that log, because it downloads it and then applies it to two distinct steps. So it can be just a small amount of data if the master goes away and never comes back up. But if the master is down, you can do a couple of situations here to have higher availability. You can do the option one, which is have your slaves provide a read-only view of the data until you have the master back up, so basically go read-only for a while. This is actually a surprisingly pretty common thing to do. It's kind of like having a master for read-write, read-only slave. Very, very simple. If the master goes down, you restore it or something like that. You reboot it, wait for the OS to come back up, and you just go read-only for a bit. You may think, oh my god, but we can't have downtime. Maybe you can have 10 minutes or an hour of downtime. However often a machine fails and needs to be rebooted, maybe that's acceptable. Because each additional 9 in availability is 99.99% and up to 5 nines and the like. Every additional 9 is like an order of magnitude more cost and people power and opportunities for people to screw it up. No matter how automated it is, there is always a way to get it wrong. So you can do read-only until the master is back. You can do an extension of that, for example, like a DRBD type setup. So you actually replicate in the block device level the master to another machine. So if the hardware dies for some reason, or you do need to take it down, you can pretty much instantly bring up another machine that's identical and continue doing read-write operations. You can also do another operation which we refer to as slave promotion. So that's basically the idea of you pick a slave and then promote it to be the master. Say, right, you're now the master. And then you sort of, the old master you now take off and sort of rebuild and repurpose as a slave or wait till it comes back up and load from back up. And this has a couple of issues. You can lose transactions not on the slave. So if the master had transactions that were committed and returned to the client, but not yet replicated, and it crashes and you do slave promotion, those transactions here that are in the extra log there, actually bringing those and applying them to the new master is tricky, to say the least, and is not guaranteed to ever go without problems. So basically, you could lose that. You can also have other issues where you have, if you have, instead of a chain of slaves, you have whole 10 slaves off the one master, and pick one for promotion. These slaves may have pulled different points in time from the master, because it's all asynchronous. There are some tools to help you sort that out and do the right thing with promotion and apply some things around. There are some tools around that, but it's not, the be-all and end-all of solutions. You can definitely end up losing a bit of data doing it that way. And it's good to think about this in various situations. For example, if you're doing financial transactions, you probably really want to be aware of this. If you're doing like buttons on a website, you probably don't really care. You'll deal with it. In fact, you may run in a less durable mode to say, don't write to disk on every commit, only do it, every second instead, and just say, I could lose a second or two of data, so be it. So it's very much, you can think about that. Usually the settings for MySQL are server-wide, so when you change those options, they're server-wide. And of course, when you're talking about slave promotion or replication, that's of course sort of replication topology-wide setup. So that's a whole bunch of fun. There is synchronous replication. Here's someone asked, what if we could replicate synchronously? So one problem with doing any form of synchronous replication is, of course, performance. Because if you wanted to do something synchronously, you now have a network hop for every commit operation. In fact, you really have to have like two-phase commit going on if you want to actually have a consistent view. And so this means you need high-speed, low-latency networks to make it work. So we're talking, gigabit Ethernet between two machines in a rack or adjacent racks, or within a data center, or at least close by fiber, not machines on different continents. Generally speaking, some people are fine with that kind of latency, but remember, you can buy all the bandwidth and high-speed links you want from here to the US. There is a fundamental limitation of the speed of light. There are certain things that Einstein says aren't getting any faster ever, and he's smarter than me. Well, at least was. and so we can't ever beat the speed of light. So there is some basic problems with physics doing this. But it is an option for some situations. So MySQL Cluster does synchronous replication for MySQL. So MySQL Cluster is a different storage engine. It's not InnoDB, so it's not necessarily a drop-in replacement. It's not suited to every workload. It has some limitations that may completely not work for your app. It actually has a very interesting model, where in fact commit is commit to memory across multiple machines. So commit actually survives machine failure. So it does survive the have you tried turning it off and on again on one machine, but it doesn't survive that for the whole cluster. So what it does is commit operation uses two-phase commit between all the nodes involved in the transaction. And so then when you get a commit back to the end user, it means this transaction is in memory on enough nodes that you could survive a node failure. If you pull the plug on the entire cluster, you may lose that transaction. Because what MySQL Cluster does is it writes checkpoints to disk every configuration option. Possibly one of the worst units ever, but you can basically configure it to be about once every second or half second or 2 seconds or something. You can write we'll do a checkpoint where the entire cluster agrees of what's written to disk. And so that's what will happen if you power everything off at once and bring it back up. If you shut down, as in type shut down, of course it writes a check then, but pull the plug. So
What happens if you do a commit on one, it commits to memory and it goes to the other machine, and then that fails to commit for whatever reason? Does it undo the commit on the first one?
Yes, because you have two-phase commit, so you have a prepare and you have a prepare phase. So basically, you have enough phases in a commit protocol that you can work out what happened in any of those situations and roll out the appropriate transactions. So basically, every single app that ever touches a database that is relational at all, that doesn't run in serializable mode, as in no one probably does, because that's single threaded, one transaction at a time, right? Every app should be able to survive transactions being rolled back for whatever reason. Lock wait timeout exceeded, hitting row lock somewhere, hitting update conflicts or node failure and stuff like that. So every app should already deal with the transaction being rolled back. How many people have written a web app that have properly dealt with the transaction being rolled back by the database? Yeah. How many people now go, oh shit, my app's buggy? And who's going, I don't really care, that hardly ever happens. You might want to log it and see how many times it does happen. It's especially interesting when you go to some of the high availability solutions. One that's out there now for MySQL called Galera will actually do multi-master writes, and the way it does it, you'll actually get, if you do sort of more conflicting writes to multiple nodes, it does it in a way that you'll get transaction rollbacks. So you start to find bugs in your app that previously were not hit as often. It's very interesting. Hopefully I will get one day Gyrus for me to give a talk on how we do wonderful database testing. We have the title of the talk already, Fishing with Dynamite. But let us just say that we enjoy quite proudly crashing database servers very, very easily. It's a bit embarrassing. Unfortunately, the state-of-the-art in open source database testing is roughly where Microsoft was in 1998. At least what they published in 1998, they may have been doing it beforehand. So we're really at the forefront and have a lot of catching up to do. But on the whole, it mostly works. We also have the option now for semi-synchronous replication in MySQL. So this was seen for a number of years now in sort of the Google patches and the Facebook patches, and it's finally actually in a MySQL release. So amazingly enough, someone writes a new feature and then 5 years down the track, whatever it is, actually gets incorporated into upstream. So semi-synchronous replication is not fully synchronous replication, and it's not asynchronous. What it does is it commits to local disk, and then it waits to return the acknowledgement of the commit to the user until that part of the replication log has been read by a slave. Right? So this has a couple of interesting effects. The end user app doesn't get the commit until the master and a slave have a copy of that transaction. But what this does do, of course, is since it commits to local disk, if the master fails and you do slave promotion, you have to repurpose the master as a slave, because it's now going to have a transaction written to disk that the end user never got an acknowledgement that actually existed, right? But the slave will actually have, sometimes. The slave may not have.
Doesn't it use two-phase commit to prevent that?
No. Yeah. It's basically, it gets the return from the slave saying, yes, I have that part of the replication log, and then it will return, hey, it exists there.
And it's having read, not having executed.
Yeah, it's having read, not having executed. So it's a compromise. It's one of those things where it's like, the whole cat theorem, you have like these compromises of nothing can provide all three. Yep, exactly. This is a compromise that may be good enough for you. So the Google guys originally wrote it because this works very well for them when they're doing slave promotion and the like, and they don't mind repurposing the master, restore it from backup, repurpose it as slave, done, continue. And this allows you, even with a manual process of doing slave promotion, you can easily get down to times of like 5-10 minutes of downtime if you ever have it. Right, it's pretty simple. Drizzle, of course, is, we originally forked it off MySQL. It looks a bit different on the end user side. Basically, some DDL is a little bit different, but most of the SQL just works. We ripped out things that really don't work for large-scale web applications. For example, stored procedures don't actually work for that, because what's the hardest layer of your application to scale? Is it the app server or the database server? Database server. So obviously what you should do is push all your logic into the database server, where it's going to be much harder to scale instead of out in these app servers, which are very easy to create. So we ripped that out, plus the code wasn't very good. And basically we've re-architected the insides a whole bunch more, so it becomes a modern C++ code base that's very modular. The kernel of Drizzle is actually of a size that a single human can understand, and you can easily write modules to do whatever the heck you want. One of the things we did do is completely re-architect replication, so it doesn't look like MySQL's replication at all. We do a very interesting thing, is we store the replication log inside the InnoDB storage engine. So instead of having a separate file that is a replication log like MySQL has, the bin log, right, which if you want that to be crash safe, actually if you want the master to be crash safe, it has to do a two-phase commit between InnoDB and the replication log on the one machine. So it actually has to do a two-phase commit between two files on the same disk, right, to be crash safe, which turns out to be a huge performance impact, so no one runs with that configuration option. and everyone just, if your machine crashes, you can end up in problems.
Yes, we do.
Yes, we do.
Yes, we do. You do.
Some people use it. But you would be surprised how few people do. Because it's like, it's faster when I change this option. Yes. Like disabling fsync, right? So what we've done is we've stored the replication log inside InnoDB. So actually the replication part of the log gets written to disk at the same point as transaction commit, which actually means that turning on replication has only a performance impact on the master of around about 10% instead of like 50 in actual real-world transaction workloads. So we get some pretty interesting benefits there by basically fundamentally improving some of the things. But on the whole, we still do asynchronous replication, which is fairly neat, just with a whole bunch of things that are improved and nice to set up. So this whole relational database space is a pretty sort of well-known problem space, and there are many brilliant people who know how to do it on small to huge scale. So one thing you can think about is, am I going to use some magical NoSQL solution or not, or traditional RDBMS? It's pretty easy to hire people who know about relational database systems and know how to optimize them, know how to write queries that don't suck, know how to architect things, know how to do master-slave, know how to do slave promotion. There's all utilities out there. It's a very well-known field. You can get people anywhere. You can hire lots of consulting firms for it. Heck, there's so many choices in relational database management systems, we can even have arguments about them. So there's lots of choices that have the same model that are relatively easy to port. I mean, SQL is a standard, in that hilarious way that makes it hard enough to port between databases that no one ever does. But, it is a standard, so it's very easy for people with knowledge in one system to translate to another. So you can actually do these kind of things on various systems. So it is a well-known problem space, and this has a great benefit if you're going to have to hire someone to look after it at any point in time. Right? There is a benefit to having something that's well understood. So, NoSQL is this great thing of being buzzword compliant, which of course is a tick box for any organization writing a new app.
No SQL in the cloud.
In the cloud would be the best tagline 2.0 beta. Web scale. It must be web scale. So I have an argument that SQL itself is not the problem. Existing relational database management systems may be the problem, and crappy queries may be the problem. But a flexible generic query language is certainly not the fundamental problem here. Having access to a flexible generic query language is actually a really powerful thing. And I want to share a little bit of a comment. So how do I query the database? It's not a database, it's a key value store. Okay, so it's not a database. How do I query it? You write a distributed MapReduce function in Erlang. Did you just go tell me to go fuck myself? I believe I did, Bob. Yeah, so, I mean, if you suddenly have the idea of someone says, hey, I want a report, and you suddenly go, I'm sorry, we have not architected our data and our entire database, our entire key value storage that way. We're going to have to write this long bit of code, distribute MapReduce Erlang, repurpose things and copy it over there. You're probably not going to get a reaction from someone who just wanted you to add up how many downloads happened in the last week. How is that hard? But you didn't consider that query in the beginning. Flexible generic query language may not be the result that you short amount of time. But hey, spawn a replication slave as an index, run the query, it'll be fine, right? But the argument comes back is, but it's web scale. There's a bunch of NoSQL arguments. So if you haven't seen this particular comment, a little YouTube video, I advise you do. It's the great thing about, at some point you get sick of fanboys on various base technologies that you want to go work on a farm shoveling pig manure, because it's much preferable to working with such people. So, there is the argument against relational databases that they don't scale is obviously rubbish, right? Many large-scale websites have relational database management systems as a core storage part of it that they rely on to make the site work, and they work fine, right? Many places do this. How many people run a website that runs with the Postgres or MySQL storage as a back end of it, and it just pretty much works fine? Yeah, even when it gets to some amount of scale, it pretty much just works fine, right? You have a flexible query language, works fine. So when someone tells you, but it's not web scale, you immediately, yeah, they're not talking something right. But SQL doesn't scale. And again, this is rubbish, because it can, because, look at the top 10 websites and how many of those we know run open source relational database servers, right? And for NoSQL solutions, I like to introduce the argument which I call, have you tried turning it off and on again? Right? So there's a difference when you're especially starting at small or even medium. It is quite possible that everything goes off at one point in time, or that your individual machine fails. And once you get to a large enough data size, copying that from somewhere else becomes a very large operation, right? 100 gig of data, isn't that much. You can't even. Well, with SSDs, you can actually buy 100 gig of storage these days, but 100 gig is pretty small. As in, copying that over the network, that actually does take some time. Going up to a terabyte, not that big again, copying that over the network does take some time. So you really want a solution that, if you turn it back off and on again, you don't have to, copy everything from somewhere else in a high availability thing. You also want to, if you turn it on and off again, for example, you have a reboot or the process crashes or something like that, you want to get back to some kind of known state. That data is, consistent to within whatever parameters you've decided are okay. Whether that means, data as it was a second ago, or 10 seconds ago, or, whatever. So, new test. Turning on and off a system should not screw you. So, MySQL itself mostly passes. MySQL with replication, again, mostly passes. MySQL with semi-sync passes, like, even more. Postgres tends to pass pretty well. Drizzle passes, even more so than MySQL. So what about NoSQL solutions? Well, remember this. Does anyone remember FSCK? And like, oh damn, machine crashed. I have to now wait, 30 minutes for an FSCK to run before I can reliably use my machine, because otherwise something could be dangling and I'll type ls and everything will explode horribly. So here's the question. Does your database have to do this? Do you restart your database server and you have to wait half an hour to run FS check, or the equivalent, database internal check, before we can use it again? Well, the problem with this, of course, it hopefully repairs the damage, right? Basically looks at structures and then tries to figure out what it thinks they should be. So it comes to some approximation of what a different algorithm thinks, what may be a common corruption case, and ways to fix it. So this whole idea of a consistent point in time, out the window. General relational database systems use a very old way of you write to a log and then you copy back. So on crash recovery, you basically replay the log and you end up in a consistent state. Be that, to the very last transaction was acknowledged to commit, or the last time a checkpoint was written, or a variety of those. Log replay, of course, can take significant amount of time. We've seen log replay take several hours, or even, 8 hours, depending on, how big the log is and how much ongoing transaction load you have and the like. Of course, running a full consistency check of, 1,000,000,000 100-byte rows and, 20 indexes, guess what? That's going to take a whole lot longer. You think file system check took a long time. For a database, it takes even more longer. Even just rewarming the cache. So what parts of the database you have in RAM is cached, that can take a long time. I know many people who load up a database server and just throw load at it but don't expect results from it, just to warm up the cache again for a couple of hours before actually redeploying that in there. Simply because otherwise, once you throw real traffic at it and expect a result in reasonable time, it's just not going to happen. Too much IO. So let's look at MongoDB. MongoDB nodes are not crash safe, as in it fails the turning it off and on again test with a single node. Not you'll lose a bit of data or the last 10 seconds. We're talking, if you kill-9 the server, it can leave your database, your MongoDB database, in a completely unrecoverable state, as in restore from backup. Right? That sound good to anyone yet? But of course, you have multiple nodes, right? And replication running. Yep, and they're not in the same rack and nothing can ever fail at the same time. So, with enough nodes and enough distributed power supply on different continents, perhaps you won't lose data. Right? It also does a wonderful thing of mmap for IO error detection, so good luck with spotting a failing disk. In the 1.8 release, they added journaling, so it does write a log. It's not enabled by default, so it is not crash safe by default. You can turn that on, but it's slow. So it's basically like running ext2 with disabled fsync. Actually, ext2 with disabled fsync is probably a better solution to reliably get some data back. But replication, because data centers have problems. Sometimes they go away. Power supplies have problems. Like the power station could just not power the entire city. That's never happened to large countries on the earth, such as the US. New York. Yeah, New York or parts of New Zealand. This has never happened at all. And it also has a very interesting part in MongoDB replication. So when a secondary connects to a new primary, it must resynchronize its position and what's been going on. And it's possible that the secondary has operations that were never committed at the primary. In this case, we roll those operations back. So it is actually possible to, when you're doing failover in MongoDB, lose transactions that were acknowledged as committed. So there's, to put it simply, it is possible to silently have MongoDB delete data without further notice that you previously thought was there. And you think, maybe this isn't so bad. But literally, I had someone who I know who checked in somewhere, and then someone messaged him saying, "Don't eat at that place, everyone gets food poisoning." Then went to look up where it was the next day to warn everyone never to go there by name. And the transaction had disappeared and now didn't know where it actually went to eat and gave horrible food poisoning for 3 days. So, it can literally give you the runs. So dev null is probably equally as durable. It's a lot faster, of course. And I highly recommend it as a great write-only memory. And I promise not every bit of the talk is ripping on MongoDB. So let's also talk about Cassandra. So Cassandra is a log-structured column family data model similar to Bigtable. It has an eventually consistent model, and it's basically designed for OLTP and serving of interactive data. It has this great config option called consistency level, which is basically for each operation you do, you get to specify a consistency level that you want. So this is, again, just think about how many people don't properly use transactions in an app. Now you get to choose consistency level for each transaction in an app. So that's going to be an added level of fun for developers. So you have consistency level of all, which is success when all nodes have responded to a write. On failure, may not have actually failed, succeed on 2, fail on 3rd. It's show fail, but 3rd will get it eventually. Fun. So you have eventual consistency and basically the idea that, you want everyone to acknowledge something exists. You have with consistency level all, that means I want very much to ensure that everyone gets this right. You have consistency level of quorum, which just simply requires a majority of nodes to come back saying they've got the right, and then that's okay, and you continue. You have a consistency level of 1, which is basically, as long as one node has it, I'm happy. So if that node fails before it's propagated somewhere else, you've lost your data, but live with it. Consistency level of any is used only for writing. Basically, a write received by any node, success. The node explodes for sending data on, lost data. So you have a couple of different modes you can choose per operation, which can be great for flexibility. You get to choose how your data is eaten or not eaten, depending on how you want it and how it appears in replication and everywhere. So you get to choose consistency and durability and everything. Great. But you have the downside of a multitude of choice and requiring application programmers to make these decisions. So CouchDB is an interesting one. It's log structured. It's append only with no auto compaction, at least last time I checked. So it has a very neat thing of recovery time is instant. Since it's log structured, you just write to the end of the file. If you crash, it opens up, goes to the end of the file, and looks at the last point that was a consistent write, and then starts the server up. So literally, crash recovery for CouchDB is within the order of a second or so. Brilliant. Only problem is, of course, a log-structured system, as we probably guessed from log-structured file systems. You write, and then eventually you get to the end of the disk. Now you've got a problem. There's no more disk to write to. So you need to then run a compaction thing, which shuffles things around, or go back and write in the middle and other such fun. So that could cause some problems. Even problems on desktop apps. Let's use CouchDB for the back end for, our social networking Twitter client thing. And then suddenly you get to the point, it's wait, where's all my disk space gone? Wait, why is CouchDB using 20 gigabytes to store my tweets? And of course, it's append only. Eventually it fills up for whatever reason. It's interesting for a couple of other reasons. It's document oriented. You have views on documents. Views are created on first read. So you have the interesting thing of you create a view, success. So essentially, create an index, success. Then someone tries to access it using that view. Then it goes on, creates it. So the first query to a view could take 3 hours. Not necessarily always what you want. Views are updated on read, not on document update. So data may be there, just take a little while to access it. Common web use case of pagination is awkward. So if you want to say, results 1 to 10, then 11 to 20 and the like, it turns out that the way CouchDB gives you an API, that turns out to be really convoluted to actually write code to do that. It's not just the lovely SQL of limit, which is not perfect by any stretch of the imagination, but it's fairly simple to get something that mostly works, which is pretty nice. Of course, there's a problem with log structure thing of, you have to do a repack or, vacuum the equivalent of, and no one's ever gotten, poked in the ribs for having to run vacuum every so often, right? It's like, whoops, disk filled out. HBase is an interesting one on top of Hadoop file system. So basically, HBase is, again, designed for a cluster. Data is written to a write-ahead log in memory, and then occasionally these logs are flushed to disk. And then this actual log is replicated to different nodes because the Hadoop file system underneath it is a replicating file system. And then the data enters a replication log where it is piped to another data center. So basically it has, every so often it replicates everywhere and replicates everywhere. HBase has this idea of region servers, and one region server is responsible for serving a given piece of data at any one time, and replication is handled by the Hadoop file system. So a client says an update to the region server currently responsible for the update key, and the region server responds with an ACK as soon as it updates its in-memory data structure and flushes the update to its write-ahead commit log. So in the trade-off comes in availability, because only the write-ahead log that has been replicated to another node is the things that are actually replicated. So there's a bit of latency going there of availability of transactions. You have to start up a new region server when it fails. So it can actually have something be temporarily unavailable for a little bit of time. But it's actually fairly useful for a whole bunch of applications. And I know some people using it very successfully for certain types of data. So, transactions. If you look at NoSQL solutions, very few of them have a concept of a transaction, right? Simple thing of a transaction, you're doing a group of changes to your data that, change it from one consistent state according to your app to another, right? And this is either all applied or not. So, well known in relational database management circles, everyone knows this from running SQL. Very simple concept. Some people say, hey, you can do everything with atomic ops. And if you read old versions of the MySQL manual, you'll see the argument for this as well. And guess what? Atomic ops are hard, right? You can do everything in atomic ops. Sure you can. It's just like you can do everything with a universal Turing machine. But there's a reason we don't program to a universal Turing machine or, in OSDC lang, for example. There's a reason we don't program that. We use other useful things. Atomic ops suck. People get them wrong. Transactions are simple, more likely for people to get correct. And no one's ever gotten crap for not having transactions, right? Transactions, very simple. Programmers will get stuff wrong and apps wrong. If you give people tools that are simple to get right and hard to get wrong, then they're more likely to get it right. Right? So you also have the argument of, but this NoSQL solution is schema-free. You don't have to create table statements and architect your data store and everything of that. Well, great. I know where everything is. Please do not touch. It's somewhere in there. It's of course. The other thing, of course, we should discuss quickly is because it's the cloud, virtualization. Virtualization solutions can, of course, screw you in new and interesting ways, where it means it can actually lie about writing things to disk again, so that fsync in the VM doesn't actually fsync on the real hardware, and it says it gets ignored in the middle because it's faster if you do that. So you can, again, have data eaten from completely not your control.
MySQL runs faster on Amazon servers for some reason.
Yeah, right. It's sometimes worth when you say, oh my god, it's so fast, to do the math, see if this disk can actually spin that fast. This is how we discovered that OS X fsync doesn't sync. When someone did the math, it's like, wait, I can't get that transaction load out of my laptop disk. I can't get that for less than $500,000 worth of storage. Turns out it wasn't actually writing to disk. So you can actually get virtualization also doing nasty things to you in there and other things in the cloud stack. So this is, once you've gotten your software perfect and the underlying storage system is perfect and all your code is perfect, you can still get in trouble down the road. So basically it comes down to two main points. There is bad software, as in the wrong choice, right? The software is the wrong choice for the job. The software could itself have, no guarantees whatsoever, and you were deluded in your belief that software should be stable, right? And you can have sort of bad people, right? As in, people write bugs, so obviously they're bad. But bad people can also make the wrong decisions. But when you have humans are fallible, humans create software, therefore software is fallible. Software is very sophisticated. It's going to have, problems with it. You also have to have people who understand the software. You also have to have people who understand the software to then write the software, because you're writing an app that connects to something else, right? So you have to have a lot of knowledge to actually have a complete picture of things. And so one of my things I want to impart is that just because something's complex and cool doesn't mean it's the right choice. You have to have a system that's understandable by humans and maintainable going forward. And so this doesn't always mean go with some bashful, cool new thing. But maybe it does for some parts of it. Having things understandable by humans is a big plus. And allowing people, because you're probably working in a team, or even if you're just doing it by yourself, which is even more important, having things as easy as possible to get right is a good thing. Because the last thing, everyone spent 2 weeks chasing one bug that was a one-line stupid mistake, right? Yep. Actually, the best one I had was a 1-bit mistake. It was the least significant bit in a byte, and that took about 2 weeks to find. Right? Smallest pad bug fix ever. Split 1 bit, lowest bit, right? So you want to be things easy to get right and hard to get wrong. And this will end up in sort of better working software. Data can be deliciously eaten in the cloud. It's not just the standard POSIX apps. You do have to think about these things. For a start, websites have gone away and not been used by anyone simply because they went down too often. This has killed multiple businesses, will kill many more. Just because someone didn't do the math on scaling, didn't think about the data storage, got to the problem of we'll just buy a larger computer, and got to the point you could not buy a larger computer for less than it costs to set up an R&D firm to develop a larger computer. So you have issues like that. So you also don't think you must jump to something distributed. Oftentimes you can just actually buy a larger computer, right? 32 gig of memory, not much of a problem anymore. So do think about this. Don't sort of suddenly think you're going to be huge instantly necessarily. Start off and have sort of a plan or a general idea to go forward. So just because it's cloud doesn't mean it magically works. It can be, just means you have more things to think about. Apart from that, it's the same story as it always been. Software and people can both give you problems. Great, thank you.